All right, good morning. So now we're going to continue in chapter 33 on light. Yesterday we talked through the definition of light, and then we also talked about and the definition being that light is electromagnetic radiation that we can see. We talked about and brainstormed a list of the various types of electromagnetic radiation. Light is one of them. There are many others. And then we talked through the propagation of light, including linear propagation, reflection, and refraction. There was a little bit of history from the 1600s where the discussion of whether light is a collection of particles or a wave. That discussion started and it continues today. Sometimes light acts as if it were individual particles. Sometimes light acts as if it was a wave. And then we finished up by learning that electromagnetic waves can travel without a medium, and then we also learned the value of the speed of light, and we're just going to use the value of 3 times 10 to the 8th meters per second, or 186,000 miles per second. And that applies to all types of electromagnetic radiation. All right, so let's continue. What we're going to do now, and then also we did touch on the speed equation, and we'll continue to use that, and when we get to the chapter on sound, we'll apply the speed equation to sound as well. Okay, so the first thing we'll do today is we're going to start off in section 33.3. That's up on page 647. So the basic topic there is the electromagnetic spectrum, but a discussion of the spectrum leads us to a discussion of wavelength and frequency. So if you could turn to page 647. And I'm going to show up on the screen the figure 33.7, which is at the bottom of that page. So here's the spectrum. Now, and what the electromagnetic spectrum does is it shows you all the different types of electromagnetic radiation, but it shows them in an order in the way in which they are related. Now, typically the spectrum is not shown in that orientation. I'm going to rotate it, and you can rotate your textbooks. Let's rotate it so it looks like this. This is the typical way that you will see it, where you have the long radio waves on the left, cosmic rays and gamma rays on the right, and then everything in between. There's a small slice of visible electromagnetic radiation, which is the light that we can see. And then you'll see ultraviolet, infrared, broadcast, X-rays, etc. Now you can see the way this graph is set up is we have 2 different scales, one for frequency and then also one for wavelength. And you'll see the frequency increases from left to right, and that the wavelength increases from right to left. So you could talk about, when you talk about cosmic rays, gamma rays, X-rays, they have a very high frequency but a very low short wavelength. as opposed to the long radio waves that have a very long wavelength but a very low frequency. So that's the relationship between all of these. Now with high frequency, you'll notice that the gamma rays, X-rays, ultraviolet all have high frequency, and those are also, as we know, the types of radiation that can cause us harm, cause us health problems. Now this textbook does not show the colors of visible light. Let me throw up a graphic of that. Yeah, here's one. I have to rotate it here. So here's a graphic that shows you the electromagnetic. So what's going on here is the visible slice of the spectrum is very, 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 very narrow. And so down here in these bars, it's just been blown up and expanded so you can see the colors. So on the right side of the beyond the visible beyond visible light to the right is ultraviolet because it's beyond violet, and then infrared means below red. So the infrared radiation is to the left of the red, or to the other side of the red. So that's the meaning of those words. You also do have a spectrum in your workbook on page 25. It's more of a pictorial one, but you get the same idea with a lot of the graphics images in this spectrum are meant to show you the relative sizes or lengths of the wavelengths. All right, so now we need to talk about wavelength and frequency. The reason this chapter does not talk about wavelength and frequency is the author assumes you already know what you need to know about wavelength and frequency. The textbook is written as if we started at chapter 1 and went chapter by chapter all the way through length and frequency. So one of the reasons that we're including this discussion of light and optics in this course is because there's a lot of overlap in terms of terminology and math calculations between these chapters and then when we get to the chapters on waves and sound. So this is, in terms of some of the terminology, this is kind of a good warm-up for waves and sound. And plus, there's a lot of other topics in physics that wouldn't be relevant to us. We could study nuclear physics. It doesn't really apply. We could study some of the mechanics chapters, but for the program you're in, that would not be necessary. All right, so let's start off with a discussion of wavelength. So what is wavelength? So anybody have an idea? You can shout it out, but I can't hear you. So anyway, what is wavelength? Well, simply you could say wavelength is the length of a wave. And you may very well have studied this and understand this from previous physics classes. So let's do a sketch of what we mean by a wave. So here's a sketch that shows a wave And it's the best way to show it. This sort of looks like what you would expect maybe like an ocean wave to look like. So you have one complete cycle or wave where the wave goes up, comes back down, and then returns to its starting point. So one complete cycle or wave. And there is a symbol used for wavelength. It's a Greek symbol. Does anybody know which Greek letter that is? That one is called lambda, and I believe that would be the lowercase lambda. But that's typically used in science for wavelength. Your workbook does have a summary of the Greek letters. If you can turn in your workbook now to pages 26, 27, and 28, there are three pages of the Greek letters. Pages 26 and 27 are the lowercase letters, 28 is uppercase, and along with the symbols and the names, you're given a little bit of a description of how the Greek letters are used as symbols in math and science. So if you can see on page 26, lambda is listed, and wavelength is one of the common uses. There are other ones as well. And then you can see some of the other ones. Alpha, beta, and theta are used commonly for to symbolize angles, and we'll use some of those. And then the uppercase letters on page 28. I'm sure in previous math and science classes you've seen the use of the Greek letters. Alright, so that is wavelength. Now let's talk about frequency. Okay, what would be a definition of frequency? Probably the simplest definition of frequency would be how often something happens. If you have an event that repeats over and over again, how often does that event repeat over and over again? Another more technical definition would be the number of waves per second. How often is a wave repeating, or how often are waves passing by a certain point? Now you'll also see another term used very commonly. Instead of the word wave, you'll see the word cycle used. So frequency could be the number of waves per second, or it could be the number of cycles per second. Let's draw another sketch of a wave. So if we were sketching not wavelength but frequency, then the horizontal axis would have time units. So if you had one wave happening every 1 second, then this distance would be or this time period would be 1 second. So that would be a frequency of 1 wave or 1 cycle per second. When you start actually performing ultrasound scans, you'll be using ultrasound in the millions of cycles per second. Now, getting back to wavelength, when we did wavelength, I just want to be clear, when I was sketching wavelength, it's actually length. So that horizontal axis for wavelength would be distance rather than time. All right, so let's get back to frequency. Okay. So in terms of frequency, what are the units that are used? So the units, when we get to frequency, are cycles per second. Now there is, as we see a lot in physics, there are units that are then named after people. So there was a physicist back in the 1800s, his name was Hertz. So we now have a frequency is commonly expressed in hertz. So the way this works is 1 cycle per second equals 1 hertz. And additionally, you'll see hertz abbreviated as uppercase H, lowercase z. So you just have to know that hertz means cycles per second. I didn't talk about the units of wavelength. The wavelength units would be really a length per cycle. In other words, how long is one wave or cycle? So for wavelength units, you'll typically see it as maybe meters per cycle, or it could be centimeters per cycle, millimeters per cycle. But I just wanted to point out to you that since wavelength is understood to be the length of one wave, you'll often see wavelength expressed as a length and the cycle unit is just left off because it's understood. But when you're doing problem solving and you're wondering why your units aren't canceling out properly, it might be because you may have left off the word cycle, because formally a wavelength is a certain length of one cycle. So we'll see that when we start working on some problems. All right, so now we're going to, we'll continue in this section 33.3. We're going to back up to the very top of that section on page 647. All right, so remember we were looking at the well, let me pull it back up again here. The electromagnetic spectrum and we saw that the way the spectrum was constructed is you have frequency increasing to the right, wavelength increasing to the left. And so what this suggests is there is some relationship between frequency and wavelength. As frequency goes up, wavelength goes down. As wavelength goes up, frequency goes down. So the relationship that in a mathematical sense is shown at the top of page 647. You can see the equation C is equal to frequency times wavelength. So we remember from the previous section, C is the speed of light. It's assumed to be constant. And in a vacuum, it is constant, and it's also the same value for all the different electromagnetic frequency types, electromagnetic radiation types, excuse me. But it's constant in a vacuum. When we get to chapter 34, I believe it is, or 35 on refraction, you'll see that when light starts passing through other types of materials, then it's not the same value. But we're going to assume that the value of the speed of light is 3 times 10 to the 8th meters per second, or in English, 186,000 miles per second. And the lowercase f is frequency, and lambda is wavelength. Now let's illustrate the use of this equation by taking a look at the example problem that's at the top of page 648. So example 33.1. So you're given that the wavelength of yellow light is 589 nanometers, and you're asked to compute the frequency of that light. Okay, so you're given that wavelength is 589. I'll write it out. The text showed you the abbreviation. The abbreviation was NM, lowercase n being the abbreviation for the nanometric prefix, lowercase m for meters. And you're asked to calculate the frequency of that light. So we're going to use the equation we just introduced. Okay, so now you're going to have to use algebra to manipulate the equation. The basic equation is shown as C is equal to frequency times wavelength. We know C, it's a constant, and we were given wavelength, so we're solving for frequency. So if you use algebra to manipulate the equation, then frequency is equal to the speed of light divided by wavelength. Now once you manipulate the equation, now you can go ahead and plug in the values. Okay, so frequency, and now since we were, and as you know, you have two different values of the speed of light. You have a metric value and an English value. We were given wavelength in metric, so let's just go with metric so you won't have to do a lot of conversions. So the first value we're going to put in is the speed of light, 3 times 10 to the 8th meters per second. I would prefer that not only numbers but units get included in equations so you can see how the units work out. And in the denominator, wavelength, so 589. And now you can see right off the bat that the abbreviation or even the word nanometer is not helpful at all. Nano has a mathematical meaning. So take a look at your inside the cover of the textbook and what is the mathematical meaning of nano. Nano means 10 to the minus 9. So that is how you're going to want to enter that into the equation, because that's the only way you're going to be able to figure this out. So 589 times 10 to the minus 9, and 10 to the minus 9 is the meaning of nano, but you still have to put in the meter unit. Now remember earlier I said that it's very common for wavelength to be expressed as a length, but the word cycle is left out, even though the formal units are the length of a cycle. So in order for this to work out, you're going to have to include that. 589 times 10 to the minus 9 meters per cycle. Now you can see that the meter units cancel out, and you're left with cycles per second. If you remember years ago when you had math and you were talking about fractions, you remember that if you're dividing a fraction by a fraction, in this case the units, and the units behave just like numbers, then dividing a fraction by a fraction is the same as multiplying the numerator by the inverse of the denominator. So the units here do turn out to be cycles per second. Alright, so at this point you now have a calculator exercise. So in this room we could have 5 or 6 different models of calculator, and they might not all operate the same. So what you're going to be trying to do is divide 3 times 10 to the 8th by 589 times 10 to the minus 9 and see if you can get your calculator to understand powers of 10. So I'm going to give you a few minutes to try to figure that out. And what I would also encourage is if anybody is struggling with it and having trouble, if some of you can help each other, kind of pull together as a group and help each other figure it out. Some people might be able to figure it out a little easier than others. Yeah. The other alternative is if you can't quite get the powers of 10 to work out in your calculator, you can do it by hand, because you've all been trained at some point in math to handle exponents. So you could do the exponents by hand, and then all you'd have to do is take 3 and divide it by 589. You're going to have to do a little bit of manipulation, maybe manually, but you can certainly do the exponents by yourself without dealing with the calculator. So anyway, the answer to this problem in the textbook is correct, and that is shown as 5.09 times 10 to the 14th, and that's shown as hertz, which is cycles per second. So if you're doing a problem like this for me, like in homework or a test, I would accept the expression of hertz, or if you just want to express it as the units as cycles per second, that's okay too. All right, so everybody take a few minutes, see if you can do that calculation with your calculator and get that answer, 5.09 times 10 to the 14th. And also remember we talked last week that the author always defaults to 3 significant figures. So that's why the expression is 5.09, because you have 3 significant figures there.
Okay.
Yours are all set?
All set? All shut down except for you.
I'll do the locking. Thank you for checking with me.
Thank you.
Yeah.
Have a good day.
Yeah. All right, so hopefully everybody was able to work that out with your calculator. If you haven't, then we'll certainly have lots of practice time to get it figured out. In the meantime, if you wanted to do the exponents manually, you certainly could do that. All right, so let's see what's next. So I am going to assign you some practice problems here. All right. Before we do that, here's a question for you. Now that we've talked about frequency and wavelength, so here's a question. I know some of you are from the State College area, some of you are not. But anyway, let me throw this out. Let's say you're either at home or in your car and you've turned the radio on. And let's say you've turned the radio on to a local AM station. In this case, 1390 WRSC. So the question is, for this AM radio station, what is the meaning of 1390? And then one other question, let's say instead of an AM station, let's say you've dialed into an FM station. And let's say the one you've dialed into is 95.3 WWWZ, a local FM station. So again, what's the meaning of the 95.3 for that station? Some of you may know, some of you may not be aware of what that is. But now that we've talked about frequency and wavelength, you might be able to guess at those. All right, so I'll leave you with that question and see if anybody can come up with that. And then here are the practice problems. The practice problems are listed in your schedule. And let me make sure you have those. So these are end of chapter problems 33.1, 33.3, 33.7, 33.9. Let me make a comment about those. Let's go to the end of chapter. So these problems start at the bottom of page 658 and go on to the top of page 659. So if you could turn to those pages and just follow along here, I just want to make a comment about these, just to avoid confusion. Okay, 33.1 at the bottom of page 658. The wording is a little confusing. I just want to be clear. You see that there are two answers given because it's really a two-part question. You're given wavelength and asked to solve for frequency. So let's treat this as, you know, part A and a part B. Part A, they're giving you a wavelength of 1 micrometer, and part 2 is a wavelength of 16 micrometers, and they're just asking you to determine the frequency of each of those wavelengths. So that's why there's two different answers. Then the other one I want to point out, which is important here, is problem 33.7. There is a typo. You'll notice in 33.7 the frequency of yellow-green light is given as 5.41 times 10 to the minus 14. That should read 5.41 times 10 to the 14, not minus 14, because that wouldn't make any sense, and you wouldn't end up with the right answer. So it's 10 to the 14 hertz, a positive 14, not a negative 14. All right, I think the rest of them are okay. And you'll also notice the problems again, 1, 3, 7, and 9. Now number 9, you'll be using the speed equation, which we had talked about yesterday. Speed is distance divided by time. All right, so now you'll also notice on your schedule that this is a double period. So what I'm going to do is you're going to get some time now to work through these problems. Typically, if it was just a 1-hour class, you'd take them away as homework and come back tomorrow, but we've got another class next period. So take some time to work these problems, and then there's another video to follow this, which will be a discussion of those problems. All right, that's it. And also feel free to take a break as you need it.